Welcome back, and in this video we're going to be looking at pH, how it's related to the concentration of hydrogen ions, and how it can interconvert between pH and concentration to pH. So you're going to need your notes, you're also going to need a scientific calculator. And we're going to start on page 7. So we're on page 7 of your notes and we're looking at pH. Now pH is actually a mathematical function. So if you're ever asked to define pH, this is its definition. It's simply just this. pH is minus log to the base 10 of the concentration of the hydrogen ions. And that's what you write down if you are asked for the definition of a pH. Now, a low pH, because this is a negative logarithmic term, corresponds to a high concentration of hydrogen ions, and a high pH obviously corresponds to a low concentration of hydrogen ions. So if we look at the scale on the side of page 7, you will see that as we change the pH by 1, the concentration of the hydrogen ions changes by a factor of 10. So that means a small change in pH actually gives you a large difference in the concentration of hydrogen ions. Substances with a low pH have a very high concentration of hydrogen ions, so they're much more likely to act as acids. Whereas at the other end of the scale, substances with a very high pH have a very low concentration of hydrogen ions, and they're much more likely to act as bases. In the middle, we have our neutral compounds. And we can see that on the bottom of page 7. So if we start with a 1 molar solution of hydrogen ions, it gets a pH of 1. And then if we change these by a factor of 10, the pH only changes by 1. So when we go from pH 1 to pH 2, we're actually diluting the concentration of our hydrogen ions by a factor of 10. So we're on page 8 and we're working out some pHs. So here I want to know the pH of a 0.2 molar concentration solution. Now I've only got the cheap calculators. Your calculators will probably work a lot better than this. But the way to do this is we go minus log 0.2 and we should get 0.6989, which rounds to 0.7. Do remember, small changes here mean big changes here. So, working out the next one, we want to know the pH of a 0.02 molar solution of HCl. So again, minus log 0.02. And our answer there is 1.698, so that will be 1.7. Notice, for every 1 mole of HCl, we have 1 mole of hydrogen ions. If we try the same thing for 5 molar nitric acid, minus log 5, and we're going to get a negative number, negative 0.7. You can have negative pHs. Anything above a 1 molar solution will come out with a negative pH. This is why pH is only valid for dilute solutions which are less than 1 molar. Otherwise you get these negative numbers. The last two, we have nitric acid, 2.5 times 10 to the minus 3. So negative log, and I'm going to just put this one in brackets, 2.5 to the minus 3. Put that all in brackets, and I should get 2.6 pH units as my answer. Notice, because this is a logarithmic scale, there are no units for this. Last but not least, the more difficult one, sulfuric acid. Now this is more difficult because it's H2SO4. So for every 1 mole of sulfuric acid, I will eventually get 2 moles of hydrogen ions. So I have 4.8 times 10 to the minus 4 as my concentration of my sulfuric acid, but that will be times 2 for the concentration of my hydrogen ions. So I have 9.6 times 10 to the minus 4 moles per decimeter cubed. So again, working out my pH, negative log of that number, my answer, and that equals 3.0. Now there's a problem with this one. This calculation here, it gives us a good enough value for the pH, but it's not particularly accurate. And to understand that, we need to look at the ionizations of the sulfuric acid. So let's look at the equations for the dissociation or the ionization of sulfuric acid. So the first ionization energy, or the first ionization of this reaction, we have H2SO4 ionizing or dissociating to produce my hydrogen ions and my HSO4 minus. The next one we have HSO4 minus dissociates into the hydrogen ions again and SO4 2 minus. So we have the two steps. So this doesn't all happen in one go. First of all, the first hydrogen ion is lost. So we do step 1 of our dissociation and then step 2 of our dissociation. Now this first step happens to completion. So we have a high concentration of hydrogen ions floating around the place, or more accurately, we have a high concentration of H3O positive ions floating around the place. Now that high concentration, if you think about what that will do to the equilibrium position of the second reaction, the second ionization. So this second ionization, you have a high concentration of hydrogen ions. This will suppress this second term. So this term will lie over more to that side. So the reason the pH we calculated was inaccurate, we say it's because this first reaction suppresses the second reaction. So by having such a high concentration of hydrogen ions from the first reaction, this pushes this reaction slightly backwards. So we can calculate the pH from the concentration of the hydrogen ions. We now need to look at calculating the concentration of the hydrogen ions from the pH. So we have to understand that pH is equal to minus log to the base 10 of the concentration of the hydrogen ions. To reverse that, I need to take the reverse logs. Now, again, if you do maths, you can work that out. If you don't do maths, you're just going to find the button on your calculator. So to reverse this, I can say that the concentration of the hydrogen ions is equal to 10 to the minus pH. And again, you're going to need to learn that. An easy way to remember it is to look on your calculator. So here is your log to the base 10 button. The inverse of this, the shift of this, is 10 to the x. So this is how I would interconvert between these two. So let's look at this first example. I want to work out the concentration of a solution with a pH of 6. So to work this out, I'm going to go shift log, because that's my inverse of my log button, minus the pH, which is 6, and I should get 1 times 10 to the minus 6, which is what I do. The next example is a pH of 3. So again, shift my log button to get the inverse, minus pH, and we get 1 times 10 to the minus 3 as my answer. Okay, so the last example is a pH with 6.2. So again, shift log minus 6.2, and I get a concentration of 6.3 times 10 to the minus 7. Now, obviously, I've only got the cheap calculators here. You'll be able to do this much better when you've got your proper ones, and give your answer in standard form, please. So we're going to have a break from pH for a minute, and we're going to concentrate on the ionization of pure water. So this is a new K value. You've looked at Kc and Kp. We're now introducing a new idea, which is Kw. But we're going to be starting from something you do know, and that is Kc. So here I have the ionization of water. So water very slightly ionizes. The position of equilibrium is well over to the left-hand side, but we can still write a Kc expression for it. So Kc, just the same as you would normally have, concentration of the hydrogen ions, concentration of the OH negative ions, divided by the concentration of the H2O, like so. Now, if we bring this concentration of the water up, and times it by Kc. This is where we get our new ionic product of water called Kw. Now, because the equilibrium position lies well over to this side, we can say that for pure water, this concentration is unchanged. So we can therefore define the concentration or the ionic product of water, Kw, as the concentration of the hydrogen ions times the concentration of the OH negative ions. And the units for this, because we've got concentration times concentration, will be moles squared dm to the minus 6, because it's concentration times concentration. So we can work out the Kw at a particular temperature, and we can also work out the pH at a particular temperature. So at 298 Kelvin, the concentration of the hydrogen ions is 1 times 10 to the minus 7. Now, because it dissociates in a 1-to-1 molar ratio, we can say the concentration of the hydrogen ions and the concentration of the OH negative ions are the same. So we've got 1 times 10 to the minus 7 times 1 times 10 to the minus 7, which gives us a Kw value of 1 times 10 to the minus 14, with the same units, moles squared dm to the minus 6. And this leads us nicely on to one of my favourite exam questions. The pH of pure water is always pH 7. Is this answer true or is this false? Well, this is actually false. The pH of pure water is not always pH 7. Now we need to explain how I know that and how I can prove that. So this goes back to something you've learnt about in equilibria, but also something we've looked at here, Kw. So if we consider this reaction of water again, so water slightly ionizing to form hydrogen ions and OH negative ions. Now this reaction is endothermic in the forwards direction. In other words, it takes energy to break the molecule apart, and that's why it's endothermic. So if we increase the temperature above 298 Kelvin, we note from our equilibrium notes that this equilibrium position will shift forwards. So this shifts equilibria forwards. What that will do is it will increase the concentration of the hydrogen ions. Therefore, concentration of hydrogen ions is increased. Because the equilibrium position has shifted forwards, I've now got a higher concentration of hydrogen ions. Because the concentration of the hydrogen ions is increased, therefore the pH will decrease. In other words, it will get less than 7. Notice that the water is still neutral. I haven't said anything about neutrality, I've just said something about pH. So water is still neutral because the concentration of the hydrogen ions is still equal to the concentration of the OH negative ions. So we still have a neutral solution, but that neutral solution is not at pH 7. It'll probably be, if we really heat it up, about pH 6.5 to 6.8.